Okay, so before we get into what's going on here, I want to talk about this. I wanted to put these at the end of the last video, but it got too long. Basically, the situation with the turtle in the previous video, like I said, was constant velocity in 2 dimensions, and these are the relevant equations. I didn't have time to map them back onto the example and show you exactly how they work, but this is basically x and y as a function of time. Okay, so this is x and y as functions of time for a 2-dimensional constant velocity situation. Okay, these are kind of like our kinematics, our equations of motion, but they're for 2 dimensions and for constant velocity. Okay, they connect velocities, positions, and times. But there's no acceleration, right? No acceleration in these equations. Why? Because constant velocity means 0 acceleration. Okay, so these are sort of what we're going to be using here. All right? And they really come straight out of the definition of velocity. So we'll come back to those in a moment. What we have here is a bald eagle getting a snack. It's in your textbook and they got this right. Bald eagles like fish. It's true. But later on, in another chapter, they show a picture of a red-bellied woodpecker and they say that it's a hairy woodpecker, but it's not. They got that one wrong, but they got this particular bird fact correct. Bald eagles like themselves some fish. So, the bald eagle starts 19.5 meters above the water. See the water here? The x-axis is the surface of the water. And the fish is very close to that surface. And the bald eagle spies the fish and decides it's lunchtime and goes for it. And drops down, moves along this line to get himself a snack. And travels at 3.1 meters per second, constant speed and constant direction. 20 degrees below the x-axis. So, let's draw this velocity vector. Remember, this is the speed and direction. Put them together, you got your velocity. So let's draw that vector. Here it is. All right, pink vector is the velocity vector. Okay. And so 3.1 meters is the length of it, meters per second is the length of it, and when I say it's 20 degrees, what I mean is if we draw that means that the vector itself is pointed 20 degrees below the positive x direction. So here's the positive x direction that way. This angle here is our theta. That's 20 degrees. Okay. And what do we, so I think that's the situation. That's it. 3.1 meters per second, 20 degrees is that angle right there. You could call it negative 20. I'm just going to call it 20 for this case. And so does the book, just call it 20 for this case. But it points below that horizontal. What we want to know, the question we're asking, is this. At what time does the eagle get the fish? We want to know what the time is here when the eagle gets the snack. And we also want to know what the position of the snack is along the x-axis. We want to know its x value. Okay. We want to know the time after leaving. Right, we're going to set the time. We're going to start the stopwatch right here, and we're going to start the timer right here. And how long after the eagle leaves the tree, I didn't draw the tree, does the eagle snag the fish? Okay, that's the question. So what I want to do here is what I did on the last part of the turtle example. We have a vector here. V0. That vector does not lie along the y-axis and it does not lie along the x-axis. That velocity vector has a y component and an x component, just like every other vector, okay, that doesn't lie along any one of the axes. Its x component is right here, right? V naught x. And remember, this is a constant velocity problem, so v and v naught are the same. Vx and v naught x are the same, and vy and v naught y are the same. There's no distinction. Okay. We just use the naughts here. I could drop them if I wanted to, but for bookkeeping reasons, we're keeping the naught. The point is that the eagle's coordinate is changing in the x and y directions. The question is, how fast is it moving in the x direction? That is the speed v naught x. Okay, that's actually the vector v naught x. I'll leave it as a magnitude though. So it's moving to the right. It's also moving down. Here's v naught y. So it's got an x part and a y part. Now this x part here and the y part there are not new vectors. They're just two parts of v naught. Okay, so there's really not, there's really only one vector here, and that's v naught. That is the actual motion, the actual velocity vector of the eagle as it approaches the snack. This just shows us the x part of the eagle's velocity vector. This vector shows us the y part of the eagle's velocity vector. Okay. So it has two parts, the x part and the y part. It's moving to the right at a speed v naught x. It's moving down at a speed v naught y. Okay. What we want to know is what, like I said, let me erase this. We want to know what time it reaches the fish, and we want to know what's the x position of the fish. That is, what's the x position of the eagle when it grabs the fish. Same thing. But I want you to think about velocity vectors like this, as having x part and a y part. Okay. Not just displacement vectors. All vectors have components. Okay. So it's moving v naught x to the right. It's moving v naught y down. Let's see, what else do we need to do? Okay, so let's actually find out what v naught x and v naught y are. Okay, we want to know what these values are. V naught x, v naught y. The idea is to use one of these equations here and solve it for time. Okay. Turns out it'll be handy to know both v naught x and v naught y, right? These are two, right? They show up here and there. We need to know those numbers. We don't know those numbers, but we have enough information to learn them. We're going to end up again solving one of these two. I'll tell you which one in a minute. One of these two for time. But to do that, we've got to know v naught x and v naught y. So let's go ahead and find them. Well, v naught x, right? If we consider this triangle here, right, here's our right angle. If we consider this triangle here, you can see that v naught x is the adjacent side to angle. So v naught x is going to be v naught, which is the hypotenuse, right? This triangle here I'm looking at, this one here, its hypotenuse is v naught. So v naught x is v naught times, it's the adjacent, so that's cosine theta. And v naught y, well, let's go ahead and find this number here. V naught is, that's 3.1 meters per second times cosine of 20. That equals, let's see, drum roll please, 2.91 meters per second. So the eagle's x-coordinate is increasing at 2.91 meters per second. As the eagle's going down and to the right, but the x-coordinate of the eagle is increasing at 2.91 meters per second. Okay. Now V naught y. Now notice something here. This is the triangle I was looking at, right? This triangle here. Boom, boom, boom. We looked at that for x, right? And we determined that V naught x involved the cosine because it was the adjacent. Well, here's the opposite side to theta, right? Turns out that this has the same length here as V naught y does there. You remember, I told you this would come back to haunt you. Maybe haunt's a bit strong of a word. You can move vectors around. You can move vectors around. They're the same vector. It doesn't matter where you move. So you can imagine taking V naught y and moving it here and completing the triangle. The length of this side is the same as the length of V naught y. And this is the opposite side. Okay, we can the side of the triangle here that we're talking about, this one here, the opposite side has the same length as V naught y does, and you can move vectors around. So I could have drawn this triangle with this vector over here, V naught y over here, pointing from there to there. So V naught y has the same length as the opposite side. Opposite is sine, V naught sine theta. But notice that this is down. Notice the vector is going down, right? Y is increasing up. So we're going to have a minus sign here. Minus 3.1 meters per second times sine 20 equals, drum roll please, minus 1.06 meters per second. So the eagle is moving to the right at 2.91 meters per second and down at 1.06 meters per second. When you combine those, you get its overall motion along the dotted line of 3.1 meters per second. Okay. Now we're looking for the time. We have these two intermediate values here. Look for the time. Now let's look. Which one of these equations do we want to use to find the time? We can't use the first one because we don't know x yet, right? That's the second thing we want to find. We want to find x. That's the second thing. We need to use the first one because we know what y is. We know y naught is 19.5 and y final is 0. All right? We know that y naught is 19.5 meters, and we know that the final position of y is 0, right? It's going to go from 19.5 meters to here, but this point here where the fish is has a y coordinate of 0. Boom. So we know everything except for time in this formula here, so we can use this one. Right? Y naught plus V naught y t. We know that y is 0. We can solve this for time. Solve this for time, do a little algebra. Time is equal to minus y naught over V naught y. Plug in your answers. Minus, let's see, y naught is 19.5 meters. V naught y is minus 1.06 meters per second. So we get a time of, let me see here, 18.4 seconds. Time. Seconds. Okay, that's the first part. Now we know the time. The second question was, what is x? Well, we can now for this, so if we can use this for the second part of the question. We got the time, now we need x. X, well, here it is. X equals x naught plus V naught x t. X naught is 0. It starts off at 19.5 meters high, but at the x position is 0. So 0 plus V naught x, which is 2.91 meters per second, times the time, which we now know is 18.4 seconds. And we get position of x is 53.5 meters. So we applied both of our 2D equations for constant velocity, and we got our answers. Okay. The main thing I want you to get out of this is this picture here. If you don't understand this picture, I want you to talk to me. Okay? I want you to talk to me. Talk to somebody. All right? I'm happy to talk to you. I'm not making that up, by the way, when I say that. I don't make that up. If you want to ask me, Dr. Wallace, what the hell's going on with this picture here? I'll be happy to sit down and spend half an hour talking to you about it. I want you to get it. All right? So, that's it. Next time, we're going to talk about not constant velocity, but constant acceleration. We've been there before, but not like this.